Hello and welcome to this Module 2 video here on a calculation that involves Exergy. This part of the video is a calculation setup and property lookup setup that I needed to solve this problem, so I'm doing it using EES since I've been preaching about it for a while already. And I'm going to use this opportunity here as well to talk a little bit about best practice in a program like EES for doing your work and just in general, good program practice. So I've already opened the application, as you can see here, and I've already started to type a little header to my program. That's when I decided, hey, I better start to turn on the recording here in order to capture everything that I'm doing, and I didn't want to just erase it all over again. But one of the things that you should do every time you start a program like this is first save the workspace somewhere in a name that, in a way that that sends to you, a descriptive name. Put it somewhere where you're going to find it. Here's my module. Here's the name of my program. And the point of doing that is that you can periodically save it, and you're not just relying on autosave for the program as you go along. We've already talked a little bit about that on the discussion board, and where how you actually save your programs in EES. Usually you would do it on OneDrive, for example, or if you have a means to map your local drive, your local hard drive to the remote desktop, then that's even better. But regardless, start everything off before you type anything else by establishing where you're going to be solving your program. So done that, we're good. Every time we want to save it now, we'll just hit the save button and we'll be in good shape. Got my little header here. This is a description of the exact same problem we've been talking about earlier on in the OneNote part of the video. What we're trying to find here is the velocity at the end of the nozzle and the Exergy destruction per unit mass that happens in that particular case. And what we did previously in OneNote is establish a system of equations that we need in order for us to solve that. And EES is going to do all the hard, tedious algebra for us, so we don't have to worry about that. So speaking of good common practice here, after when we start to program with this thing here, I strongly advise you to start immediately to look at your unit system for the setup. And when you do that, make sure that the units that you got make sense. So this problem was in SI, so that's good. Temperature units, I'm going to keep them in Celsius here, even though, as we'll see, everything is given to us in Kelvin. The reason I'm going to do that is because the functions that we'll be using in this problem require an argument that's in Celsius. So I want to make sure I got that one checked up here. I took the pressure in bar because that's what's given to us in the problem. And actually we're given both bar and kilopascal, right? 1 and 2 is in Pascal, and the dead state's in bar. So I'm going to stick with kilopascal. I'm changing it right now. Let's keep that in kilopascal, and I think everything else is okay. Energy units in kilojoules. We'll have some comments to make about this a little bit later. A bad trap that could happen there. All right, let's get going. So step number 1, along with our 5-step process, although we're not going to follow that entire thing over here in EES, but it really pays to just list what we know in terms of givens before we do anything else. I always love that word, the givens. So we have a temperature at the inlet to the nozzle of 1300 Kelvin, a pressure of 360, and that's in kPa. Notice that I'm putting my unit straight into the program right there, although we're going to go to the variable page later to augment that as well. But it's nice to have it right in the page so that so that we can see what it is without looking anywhere else. And the syntax for doing that in EES is square brackets around the units after we've defined them. So there we go. So that looks like it's good for the pressure. The velocity of the inlet is given to us as 10 meters per second. Go. At the outlet, I'm just going to continue on without adding any more comments here. At the outlets, it's 900 Kelvin and a pressure of 130 kilopascal. Stop me if I'm making a mistake. Kidding. You can't stop me. The video. The temperature of the dead state is 293 Kelvin, so 20 degrees Celsius. Okay, and we're done. I think this is all that was given to us in this particular problem. Now let's work on our analysis based on what we've highlighted in the OneNote video of this problem. The analysis asks for, let's see, finding the specific heat at constant pressure. And so we need to figure this out for argon. How do we do that? Well, in EES, when you're not sure what function gives you something, you go to the function information button, which is this button right here on top of the page, which I think you can also find it somewhere else too. I can find it somewhere else as well. There's usually a bunch of places where you can find everything in EES. Function info, there you go. So there's another way of getting the very same menus of options for functions for information. To pull down options and go to function information, or this button right there, same thing. Now I'm interested in thermophysical properties. I am dealing with an ideal gas, and it immediately populates the table with a common series of functions, and immediately I see that I got a CP function right there, which I'm very interested in. I'm going to highlight argon as my gas. And I see I was right earlier that what it wants as an argument is a temperature in Celsius. So it's good that I set up my unit system in Celsius back down there. And it gives me a nice example of syntax for doing that, which suits me just fine. It's exactly what I'm after. Again, there's a lot of different databases in EES. If you didn't remember the symbol CP for what you're looking for, you could actually also look, I believe that there's a separate function that should give us the same thing called specific heats. Oh yeah, there we go, specific heats. So specific heats for argon, same syntax. I can't imagine that the function is the same, but we could check it out. Function specific heat, just a nice blur about this. Didn't really tell me where it's from, but anyway, I thought I'd show that up. Versus the CP function info for that guy. Returns constant pressure and provides exactly the same results. There you go. So this answers what I was suspecting. There's two functions that call the exact same thing. CP. So I'm going to use the CP function as I've got there. Since I need it twice, I'm going to hit it twice. I need it twice because I got two temperatures, right? I got T1 and I've got T2. Now, I know I'm making a mistake here, right? Because T1's in Kelvin, and as is T2, and I've just looked up the function information. It does not want the temperature in Kelvin, it wants it in Celsius. So I'm going to make a new variable I'm going to call T2C. I'm simply going to convert T1 and T2 to Celsius, before I pass it through to this thing. I'm going to give these guys a different name, CP1, CP2. Okay, give me a little spacing here so I can breathe. And now I need to define my T1C and T2C. So let's do that. T1C, I'm going to use a function called convertTemp. ConvertTemp. Okay, and I know that function already. Let's look it up again. Since with this, there should be a function here. Yeah, there we go. ConvertTemp is right there. That's the function I'm interested in. And here's the way it goes. T is convertTemp from C to Fahrenheit. Give the temp in C that you want to convert. If you're not sure, again, hit the function info button, and it tells you exactly the information that I just told you right now. Okay, so we're going to use that command, and we're going to use it twice. I'm going to paste it again. Just throw it right there. So T2C, equal to convert temp from Celsius, I don't want it from Celsius, I want it from Kelvin to Celsius. And the temperature, I want to do that for T2, of course, T2, which is Kelvin. So from Kelvin to Celsius. Similarly, over here, from Kelvin to Celsius, T1. That's going to be T1C. All right, so I'm looking good now for my CP and my CP1 and CP2. Spoiler alert here. Argon is a monoatomic gas. Monoatomic gas are really ideal gases, meaning that their specific heat really doesn't change as a function of temperature. So the fact that I'm calculating CP1 and CP2 twice, for the two different temperatures, I'm really not expecting any difference. If you start seeing differences when you're in specific heats, when you're dealing with monoatomic gases, you're probably calling the wrong function or doing something. It should be a constant. So we'll see. We'll verify, right? EES is going to, actually, we can just do it right now. The program should work. 10 equations, 10 variable, no problem. Let's hit the calculation button. It's a good place to do a test here. CP1, 0.5203. CP2, 0.5203. Here you go, 4 sig figs. And everything looks really, it's dead on. This is a good place to check out the fact that we've got some potential unit problems. Okay. T1C, dimensionless, and convert C, of course, spits back at temperature in Celsius. So I need to define my T1C and T2C. Specific heats affect the temperature input with units of C, but the units are dimensionless. So they're all related to the fact that T1C and T2C are not defined in terms of unit. Let's take care of that immediately. And we do that using this variable info box. And here I see all my units, and I clearly see what's missing here. So CP1, that's a specific heat, so therefore the units are going to be in SI, kilojoules per kilogram Kelvin. And notice that the multiplication on the denominator in EES is a dash. So it's kg-k to mean kilogram times Kelvin on the denominator. Neat little trick here. If you've got to copy a bunch of units to different places, you can just drag that little bullet and boom, it copies it down. So if I had like 18 different CPs there, I don't have to type it 18 times. Kind of nice. T1C, that's my guy in Celsius. T2C is in Celsius. And you notice that the other ones that I define using square brackets are naturally populated there, so everything looks good. So now if I hit the calculation button again, I shouldn't get these errors. Hopefully these errors will have gone. And voila, look at this, no errors. What a country. All right, okay, so moving on. We've got our analysis nicely started. Let's keep going. What else did we need? Oh yeah, we needed the enthalpy. The enthalpy of the argon at the inlet and the outlet. And since it's an ideal gas, I'm going to use the CP1. And at this point, of course, I can just use CP1 or CP2 all the time because they're the same. In fact, I'm going to make my life a little easier here. I'm going to define a variable CP, which is simply CP1, which is CP2. So there we go. And EES is not case sensitive, so I can call this guy capital CP there, and I think that's just fine. I'm pretty sure that that's right here. Let's just check just for fun. Do that. Yeah, there we go. It doesn't make a distinction between lowercase and uppercase on the variable name. So if I call it once with a lowercase, I think it's going to pick that up. I'm going to put it there as a uppercase, just so it's easier to read, but it's all the same. And now I'm going to multiply that by T1. So question for you, stop the video after the question. Is that T1 in Kelvin that I want there, or T1 in Celsius that I want there? All right, even though, I've got my unit system defined here, what do you think? What do you think is the proper temperature here? 5, 4, 3, 1. Always use an absolute scale when you're multiplying, manipulating, doing a multiplication or a division manipulation of temperature. Must be an absolute scale. It makes no sense to multiply with the Celsius value here. So this guy's got to be in Kelvin, and my T1's in Kelvin, so I'm good. H2, same thing, so it's going to be my Cp times T2. Looking good. Now, since we're in EES here, do we really need to use this as an ideal gas? There must be a function under the specific thermophysical properties for ideal gas that deals with enthalpy. Let's see, and sure enough there is. There's a bunch of enthalpies. Later on, towards the end of the course, we'll talk about enthalpy of formation and fusion, or formation specifically, sorry. And however, in this particular case, what we're interested in is the enthalpy of argon. Notice that it's only a function of temperature. And so, just for fun, let's calculate a second way here and see what goes on with that. Let's see, H2 and T2. Oh, but wait, this guy, what did it want? It wanted Celsius. So let's make sure we pass it the right variable here. I'm going to repeat this here for state 1. H1, 2. So I've got I got two H1s and two H2s. Okay, and we'll see what that gives us. We can talk about that later. Okay, coming along nicely. Next is the equation, the result of the conservation of energy that we had, which told us that the enthalpy, the total enthalpy as it's called, at the inlet must be equal to the total enthalpy at the outlet. And that particular expression was H1 plus half V1 squared is equal to H2 plus half V2 squared. All right, you wanted to say that. Okay, let's put the little sign so I know that he's not going to like that. Okay, all right, that's the expression that we found in OneNote in our derivation. That should look pretty good. That was an important expression. I think that was our equation 3, I believe, if I'm not mistaken, from the previous video. And next we need the entropy, the specific entropy at both ends in order to find part B, our Exergy destruction per unit mass term. So S1 is equal, now I need an entropy function. Pretty sure we're going to find one, right? We're getting good at this. There we go, entropy. So I got my argon selected. I noticed that my temperature's got to be in Celsius and my pressure in kPa. I'm looking good. Boom. Over here, keep this one. I'm going to get rid of that. Argon T is equal to 1C, and the pressure is equal to P1. Okay. And the entropy at state 2 is going to be the same thing. T2 and T2. Okay. And of course, for an ideal gas, I could use a TS is equal to DH minus VDP type relationship, which I've highlighted in the other video. I could do that as well. Just as good, but I'm going to do it this way since I've got access to EES here and it's kind of more straightforward. Finally, the question B was the Exergy destruction rate per unit mass. So I'm going to make up a variable here that kind of makes sense to me, and I'm going to repeat the equation that we derived. In the OneNote video here to do this, which is change in enthalpy between state 1 and state 2 minus entropy term which was T naught times, and remember when we're doing multiplications with temperature, must always be a absolute scale, so Kelvin, and T naught is in fact defined as Kelvin, so I'm going to be safe here. Here's my S1, S2 that E should find for me, plus V1 all squared minus V2 all squared. All that divided by 2 or multiplied by 1/2. Okay, and I think I'm in good shape here, right? We all done? Let's start by saving. Hit this button. Button next. 19 equations, 19 variable, no syntax error. Oh, this looks perfect. Well, I've got our little unit problem here, but let's not worry about it just yet. And hit the solve button, and of course we've got some unit problems. Here's our CPs from before. That looks good. We'll add that. Here's the answer. ED over M dot. Of course, I should work on my formatting here. It's not very pretty. 6.054. And H1 is this. The second H1 is not the same. Who is this? This is again using the ideal gas law, CPT. And this is using enthalpy function. So that's not looking too good, right? Why are our enthalpies so off on both sides? Well, we'll investigate this a little bit more in a moment. Let's just keep going. Pressure 1, this is the stuff I was given. Pressure 2, this is the entropy lookup. I really got to put my units there to feel better. And everything else. And looks like the flow is accelerating from 10 meters per second to 22.7 meters per second. I really think you're going to have a nozzle that's going to accelerate the flow by factor 2 only. It seems like a pretty worthy nozzle to me. Okay. Right, so let's start by fixing those units. This is always bothers me. That's always a good way to find problems. So again, I'm going to grab that guy and go up. The Exergy destruction term, that's going to be in kilojoules per kilogram. So I'm going to get rid of that K. Similarly, for the enthalpies, they're all going to be the same. So I'm just going to copy that in there. Add on. My pressure is in kPa. Good. My entropy is in kilojoules per kg Kelvin. So let's put that in there. And my speed should be in meters per second. Alright, so that should really clean a lot of my units. Up, 19 equations, system and variables, everything's populated here, looking good. Let's hit the button. Oh, let's save first. Let's hit the button, and I still got 2 potential unit problems detected. But everything is looking good, right? My units are all posting. Okay, let's take a look at what it's saying. Ooh, and this is a very interesting and important one. This is one of the things I really wanted to highlight. So, our unit system is in SI units with kilojoules as the basic unit for energy, right? Well, the units of energy, of course, are going to be very key for calculation of enthalpy. So this enthalpy H1 right here is in kilojoules. But when you're multiplying meters per second together, squaring it, to find the dynamic enthalpy, you're going to get basically a value of this enthalpy in joules. So I'm adding here kilojoules with joules. That is a bad thing, not kosher. So either I change this guy to joules or I change this guy to kilojoules if I want to get things right. Since the values that I was looking for were all in kilojoules, I think I'm going to stick with the kilojoules, but I can do either one and it's going to be okay. Similarly with the Exergy destruction term, I've got that same problem because I've got these velocities here, which output something in joules and everything else in kilojoules. So let's fix that. Let's go back to the problem. It's an important one. Okay, so I'm going to have that here. So I'm going to turn this guy, which is in joules, into kilojoules. Of course, I've got 1,000 kilojoules per joules. So if I want to convert joules to kilojoules, I got to divide it by 1,000. So I'm going to divide it by 1,000 just by adding it there. And similarly on this side right there, I'll just do the same thing. I'll divide it by 1,000. Divide that guy by 1,000. And that should take care of my kilojoules to joule problem. And of course, it doesn't know that, so I'm going to have to force the program to realize that I've gotten it right. So I fixed this. They don't differ by 1,000 anymore because I've got taken care of it by doing the conversion manually myself. So I'm going to disable unit checking for that guy, and I'm going to disable checking for that guy so that EES does not scream at me. This is particularly useful if I've got many errors that I'm trying to deal with. You want to fix them one at a time and not have it pop up all the time. So now it looks good. I don't have any more unit problems, and I can keep looking at things. Did anything change? Oh, I'm noticing that my V2 is now not 22 anymore, something like that. It's 650, which is a number that seems to make a lot more sense for a nozzle, certainly. So that's looking good. So changing that factor of 1,000 made a big difference, obviously did. Everything else looks okay. Oh, we still had this problem with the enthalpies that didn't match, right? When we were using the ideal gas law versus when we're using the enthalpy call. So very often what happens, especially in an enthalpy call, is where the zero enthalpy is defined as. When we apply the ideal gas, ideal gas model to finding enthalpy and define H1 to be Cp times T, implicitly we made a datum of enthalpy to be absolute 0 Kelvin, right? H1 is equal, or H is equal to 0 when T is equal to 0. That's not necessarily the case for this guy right there. Typically, enthalpy data tables use a reference temperature at which they define the variables to be 0. And it's not entirely clear just by looking at this what that reference value is, but it's definitely a higher temperature than this guy right here, just based on the fact that the enthalpy reference value is higher. One way to make sure to verify that it's okay is to check the difference in enthalpy and make sure that the difference in enthalpy remains the same, right? Because if there's a datum, it's going to, if it's a datum offset, it's going to simply, subtract the datum on both sides, and we'll end up with the same value. So H1, the second value of H1 and the second value of H2 together is the difference between these two guys. Let's call that delta H2, right? The second delta H is what I mean here. And I'm simply going to copy that right there to do the same over my ideal gas law one. So delta H1 is equal to H1 minus H2. Does that make sense? Okay, so what I'm saying is that if it's just a datum variable property issue, then the delta H2 is going to be equal to delta H1. So let's save that. Let's go and do it. And what do we have? Delta H1 is 208.1. H2 208.1. There you go. So we've got, it's just a matter of datum that defines the enthalpy value in the table for the enthalpy call function to be 0. And it's probably, I'm guessing, 0 at 25 degrees Celsius. That's typical reference date for these enthalpy calculation types. Let's check it. I just arbitrarily changed the temperature for H12 here at 25 instead of T1 in Celsius, but just because I want to see what that temperature is, what that enthalpy is. And well, yeah, there you go. So enthalpy now at 25 degrees Celsius is 0. So we've solved the mystery. The reference temperature for enthalpy for an ideal gas, 25 degrees Celsius. Okay. So I'm going to save my program with the right value. Check it one more time. And where's my deltas? My deltas are back to okay. Everything's good. Good. I think that's. Oh, I still delta. Let's fix that over here. Some kilojoules per kg. I'd like to make sure that the program is all kosher before we get out of it, and by that I mean I want to see no unit problems. No unit problems. Nothing else has changed. Okay, to recap, her velocity is at 2 is 645. That's that was part A of the problem, and the Exergy destruction term is 6.05 kilojoules per kilogram. Voila, problem solved. Hope you've enjoyed this overview of ease in solving a thermodynamic problem. A little lengthy, but I think it was worth the explanation. Hope you enjoyed. Take care. Bye-bye.